Hey there, it's Miss B. In this video, we're looking at the Unit 1, Lesson 19 cumulative practice problems. So there are a couple questions we're going to skip, like number 4. So just keep that in mind. Otherwise, let's dive in. So this first question, we have just what is the measure of angle ABE, and how do you know? Well, there's a very long-winded explanation for this, but I'll do my best to try to make it short. First things first, I am going to label A, B, and E. I am just going to connect those letters in that order. So that means this angle right here. And what we want to know is how many degrees that angle is. And the short answer to this is that it is 40 degrees. The long part is how do you know? So these two angles are called vertical angles. And we have two different ways that we can actually prove that they are going to be the same measurement. So the first way involves translating. So if I have the ray that extends from B to E, we can actually reflect this, or I'm sorry, rotate it, other R transformation word. We can rotate this 180 degrees and it will line up with this ray here, since we know these are two straight lines. We know that it'll, after a 180 degree rotation, end up here and go this way. So it'll map onto C. Likewise, if we have a ray that's coming from coming from B and going towards A, we can also rotate that one 180 degrees and it will land here on this right here. Since this makes 180 degree angle, it maps onto D. So rotating both pieces of this angle maps it onto this angle right here. And since we know that rotations actually preserve angle measure, we know that if it maps onto it, it means they have to be exactly the same size. Now, that's using transformations that we've learned throughout this unit so far. What I like to use for my explanation here relies a little bit more on algebra. So I'm going to use that explanation. I'm going to highlight a couple things here and try to color code a couple pieces, so stick with me. First off, I'm going to use green to represent this straight line here. And I'm going to use yellow to represent the other straight line here, just so that you can see which pieces I'm referring to as I actually, talk about these different things. And I am going to use blue for something else, but you'll see that in a second. So I'm going to use my laser pointer a little bit just to talk about this. This green line is 180 degrees. A straight angle, a straight line makes 180 degrees. That's just our fact that we're working with. This yellow line also makes 180 degrees because it is a straight line. You may notice, though, that we have an overlapping area where the green and the yellow make up an angle together. One that is not the angles in question that we're talking about here. So this is the angle that I'm going to actually label as my blue piece. And this is angle ABC. So this is going to be my blue highlighter piece. Actually, I'll just kind of highlight A and then B and then C so you can see the actual angle I'm talking about here. Okay. So using some algebra, we're just going to express that these things need to add up to 180 degrees. So I can first say my equation for my green line, that the measure of angle ABE, so that's the red angle that's drawn there, the one in question. If I add that with the measure of angle ABC, the blue one, they need to equal 180 degrees. I also can say that same thing about my yellow line, but first things first, whoops, that's not green, this is green. This is my equation of my green line. This piece is my blue angle. So to represent the yellow line, we can say the measure of angle, and we'll say CBD, that's the other 40-degree angle. And when we add that with the measure of angle ABC, that also needs to make 180 degrees. So this is my yellow line, defined by this, but it's also including ABC, which is that blue angle, so I have that in both of them. Well, conveniently enough, they're both equal to 180 degrees. So I can substitute in one of these for the other. I can actually say, if I put both of these together, we can say the measure of angle ABE plus the measure of angle ABC should be equal to measure of angle CBD added with measure of angle ABC. Because I knew each side was 180, I essentially have 180 equal to 180, so I know that this equation is legitimate and I'm allowed to use it. So this was my green right here, and this was my yellow. I'm saying, hey, those are both lines, they should both have the same number of degrees in them. Now, since we do have a piece in common for each, that is ABC, we can actually subtract ABC from both sides. So I am going to subtract the measure of angle ABC from each side of my equation, because it should be the same as itself. It should not ever change. There is nothing being done to it that would make it change. It just is the same as itself. It's the same as subtracting 5 from both sides of an equation. 5 is always going to be 5. In this case, ABC will still be ABC. So what we have left then is that the measure of angle ABE is going to be equal to the measure of angle CBD. So this means that my red angle here is equal to something that was 40 degrees. So this is how we know, using algebra, that those two have to be equal to each other. And we don't have to have that CBD is equal to 40. It works with any angle measure. So that is the algebraic way of showing this. We can actually substitute in here then and say measure of angle ABE is equal to 40 degrees and actually show an answer using some algebra. So that is how I know. Now, that was a long answer, but hopefully it made some sense, especially if you missed part of our lesson on this. Let's look now at question 2. We are going to select all true statements about this figure. Also, you may hear my cat in the background. She's just saying hello. So select all true statements about this figure. C plus B equals D plus C. Well, let's look at some of our smaller things. When they're using these lowercase letters, they are saying those are these angle measures here that are also using lowercase letters. Because they are degree measurements, they're actually representing specific values. So C plus B, that is right here, C plus B. And D plus C, I agree. That is true. That is literally what we just talked about in the last question, which is how we know. So I would say this piece here is true. Now, part B, or option B, says that D plus B is equal to 180 degrees. D is here and B is here. These are angles that are vertical from each other. Vertical angles, like we just looked at in our last problem, those are congruent to each other. So no, these two should not add up to 180. We don't know that. Especially because it would work if they were both 90. My cat she just really wants to say hello, so I don't know. I don't know if you can hear her, but I guess she's just saying hello. Hi, Winnie. You're a good girl. We're going to get back to doing some math. Okay, so these are not going to be equal to 180. Let's look at C and D. Rotate clockwise by angle ABC. So this one here. Rotate clockwise by angle ABC using center. It actually didn't come out here, but it should be using center B. It just didn't print well in this document, so I'm sorry if that's also missing from yours. Using center B. Then angle CBD is the image of angle ABE. So let's look at this on here. Rotate clockwise by angle ABC using center B. Then angle CBD is the image of ABE. Not gonna work because we won't have things overlap here. We actually do have to rotate, but we can rotate by 180 for this entire figure. So this one isn't gonna work for us. This one here, the next option, is the 180 degree choice. Rotate everything 180 degrees using center B. Then angle CBD would be the image of angle EBA. This is the transformation version of proving that vertical angles are congruent. Let's look at our option E. Reflect across the angle bisector of angle ABC. Okay, so let's look at ABC. That's this one here. So they're saying reflect across the angle bisector. And then angle CBD is the image of angle ABE. Yeah, I would say this works as well. I actually kind of like the reflection proof a little bit better, but the translation, or the rotation version of this, I think is the most commonly used one. So, but that does make E correct as well. That does mean for us also that F is now incorrect, because the way to actually do this correctly is to reflect across an angle bisector. F says to just reflect across line CE. And line CE is this one. If we reflect across it, we're going to end up with like this as our other line, and things are not going to map up. So, not going to work for us. Not today. Sorry, option F. Okay. So that is it for that one. It's A, D, and E. Moving to question 3, we have point D is rotated 180 degrees using B as the center. Explain why the image of D must lie on the ray BA. So, let's talk about this rotation. Point D is rotated 180 degrees using B as the center. So, we can say oops, that pen is a little too thick for me, because this is a little bit of a longer explanation. Actually, I'll walk you through it first. Basically, if I'm going to rotate D 180 degrees, it's going to lie on the same line. We're going to end up calling it D prime. So we're going to have D prime And that means that D, B, and D is 180 degrees because an angle formed by a point, the center of rotation, and the image of that point will always create an angle that is congruent to how far it was rotated. Basically, it's going to make a 180-degree angle if we rotate it 180 degrees. So that means they do have to form a straight line right here. And so because it has to lie on the exact opposite side of B, it has to lie on this line here, which is BA. That is a long-winded version of that, which might just seem like it makes sense to begin with. And why do we even need to say that? But in geometry, we always want to prove things. And so we're sort of proving that this has to be the case. So let's say rotating D 180 degrees around B creates a point D prime. By definition, the measure of angle DB D prime, so that's the point, the center of rotation, and the image of the point, is equal to 180 degrees. This means they make a straight line. So D prime must be on the opposite side of B from D. It's actually important that we say that it's opposite from D. I was just thinking by default it's opposite, but it needs to be across from D on the other side. So D prime must be on ray BA. That is the way that we would write that out. So yeah, that is our written explanation for question 3. Now question 4 on this assignment, we are skipping, so you'll see down here, we're skipping question 4, which means we're going to move on to the next page to question 5. Now this is about quadrilateral. I want to zoom in on the picture, but let's actually read the problem first. Quadrilateral ABCD is congruent to quadrilateral A prime, B prime, C prime, D prime. We are going to describe a sequence of rigid motions that takes A to A prime, B to B prime, C to C prime, and D to D prime. This is something that we encountered in lesson 17, and you actually see that right here. So I would say that the first thing we're going to do is translate so that some of these points land on top of each other. Specifically, we're just going to choose a point. We can use A, B, C, or D. It doesn't matter. I like to just start with A. It's the beginning, I guess. So I can say translate A, B, C, D. Now, there are 2 ways to say this. In my class, we talked about how using so that the 2 points coincide. The other way to say this is translate A, B, C, D by directed line segment A A prime. So let's actually use that description here. By directed line segment A prime. The other way to say that is so that A coincides with A prime. So that's your alternate. Either way, both of those result in A and A prime being in the same spot, and that's what coincide means. So now we just need to do some rotating because both of these, actually skipped this part mentally first, A, B, C, and D, these go counterclockwise around, and so does A prime, B prime, C prime, and D prime. And if we have our letters going in the same direction around the outside of our shape, what that means is we don't need to do any reflecting to change our order. So we're just going to translate and rotate. That's really what we have. So we translated it. Now we're going to rotate the image. And I know I used A and A prime, so I have to say rotating the image around A prime. Whatever point you used to translate onto its image, you have to use that as your center of rotation. So rotate the image around A prime. And then we're going to say until, and at this point, we can choose any other letter except for A, because A is the center, so we can choose B, C, or D. Let's use C just to mix things up, so I'm not just using A and B. So until C coincides with C prime. And that's it. That is our whole sequence of rigid motions. So if we move to question 6, we're also going to describe a sequence of rigid motions. And this is also from lesson 17, and it's going to be essentially identical here. As long as we check A, B, C goes clockwise, A prime, B prime, C prime also goes clockwise, so we don't need to do any reflecting. We're going to use that same process. I am going to say translate. Let's use B here instead of A, just for fun. Translate B. Now you can say so that it coincides with B prime, or you can say by directed line segment B, B prime. Those are equivalent. I'm going to say B. I'm sorry, we want to translate not just B. We want to translate A, B, C. So that B coincides with B prime. The other way of saying this, just for, transparency, is bidirected line segment B, B prime. Now we're going to rotate the image around B prime until, let's say until A coincides with A prime. You also could have chosen C here, and that answer would be correct. We just have to choose one of the other points of the triangle that isn't the one that we translated on originally on top. Okay. So let's go down. This one here is a question from lesson 15. So a different answer here. Instead of just that same transformation sequence, so in quadrilateral BADC, we have the following properties. So AB is equal to AD, and BC is equal to DC. I'm going to label these with some markings on my drawing here. I'll use red so they stand out. AB is congruent to AD, and then BC is congruent to DC. So right here. That makes this shape a kite. It has two sets of congruent sides, but they are not across from each other. They're actually adjacent to each other or next to each other. So for this one, they're also telling us the line AC is a line of symmetry for this quadrilateral. So I'm going to draw in the line AC. Okay, that is a line of symmetry. So based on the line of symmetry, explain why the diagonals AC and BD are perpendicular. We know that if this is a line of symmetry, that means we can reflect across it, and the pieces will map onto each other. Reflecting across, let's say reflecting B across the line of symmetry will take it to D so by definition, because that line of symmetry creates or perpendicularly bisects the image and the pre-image, D is essentially the image and B here is our pre-image. So we can just say by definition, it's the perpendicular bisector. And we'll say it's the perpendicular bisector of BD. Okay, so the second part of this is based on the line of symmetry. Explain why angles ACB and ACD have the same measure. That is this angle here and this angle here. So we want to explain why those two have the same measurement. It's going to be a similar explanation to the first one. We're going to say that reflecting reflecting using this line of symmetry takes B to D while keeping A and C in the same place. And because it preserves angle measure, it will take ACB to ACD. So it's essentially going to take that blue angle and reflect it onto the green one. And we know that performing that reflection keeps the angles measures the same. So if they land on top of each other, they must be congruent. So we will say, whoops, reflecting across the line of symmetry. We'll just say will take angle ACB to angle ACD. We know they will have the same measure because reflections preserve angle measure. Okay. All right, let's keep going. Because if you don't see it here, there's actually the title for question 8 is down here. Here are 2 polygons on my page. I don't know if it ended up on the correct spot on your homework page, but on mine it's down at the bottom here. So we're going to keep going to the next page. Here are these 2 polygons. So we want to then follow the directions below, which is to select all sequences of translations, rotations, and reflections that take polygon P to polygon Q. Now, let's actually look at what this is. This would be easier to do if I had patty paper, but I am going to at least sort of trace over this shape here. Let's see if I can get it to snap right to it. Nope, it thinks it's a square. Oh darn. Well, that's okay. I'll freehand it as best I can. Oh, I have a better idea. If I snap all these lines by making them, I think I can still create a polygon shape without, or with a center. Yeah, it'll still make it filled in for me. So my red shape here is the pre-image because that is polygon P. We are going to take that to polygon Q. So if we reflect this over line BA, I can't actually use my lasso tool here to, I might be able to flip it, but I can mostly use this to translate and to rotate. Now technically it resizes, but I'm going to keep the size the same as much as I can because we're not changing size on things here. So if I reflected this over BA, I'm just going to sketch where that would land. So that's this line right here, meaning I would kind of have this, oops, I would have this, and then this here, like this. And this blue shape would be my new piece. And then translate by directed line segment CB. CB is this right here. So that's just going to mean take my blue piece and move it downwards. Definitely think it's not going to land where it needs to be, which is over here to the right. So not going to happen. So which means this one is not correct. Doesn't work. Let's look at B. If we translate by directed line segment BA and then reflect, I think that's going to work for us. If we translate by directed line segment BA, that means taking B and placing it where A is. And now if I reflect over BA, that is going to map my red polygon onto the green one here, or basically it's going to take P to Q. So yes, this one works. Let's move this back to its right spot where it's going to start out so we can test the rest of these. C says rotate 60 degrees clockwise around point B and then translate by directed line segment CB. So directed line segment CB is still this vertical right here. It's basically 1 unit, 2 units straight down. So I can rotate. It's a little hard to do a center of rotation here. This actually defaults to being symmetrical, but I know that a rotation should still take me 60 degrees. And if we're rotating around B, then B should not move. So if we want to rotate 60 degrees, 60 degrees means we're actually just going to go this distance here, or one triangle. So let's take this guy and see what we can do with it. Which I believe means it'll take me right about here. And B should not have moved, so I believe that's here. It always ends up moving. Oops. So now they want me to translate this 2 units straight down. That lands it here, not quite lined up, so not going to work for us. All right, let's cross that one out. Option D is to translate so that E is taken to H and then rotate 120 degrees clockwise around H. I think we can do that. So let's translate here. E is the center point where there's like a little dent, and so that it is taken to H. I can do that. They now say rotate 120 degrees clockwise around point H. All right, well, let's rotate 120 degrees. That should be 2 triangles of rotation. And because this actually lines up with a line here, clockwise means this should go 1 and then 2. Okay, I see what this is going to do. It's not going to quite work out, but we can still try to rotate. It's going to be something like this. We're actually going to have these middle pieces should be lining up if we did that correctly. It's just difficult for me to do that with this shape. We'll have something like this. Not going to work. It would need a reflection then to like finish it off across this line right here. So yeah, just not going to work for us. Oops. Didn't mean to undo that one. So not going to work. Let's look at the last one. Translate so that A is taken to J, then reflect over line BA. I think this one works. Let's translate so that A, so that original point, is taken down to J. Yeah. And then reflect over line BA. That is this line right here. And yes, that absolutely will reflect this shape across it and land on the other one. So these two, B and E, are both correct. And that should be the end of our homework here. So I actually, yeah, it is, because I don't have any problems below it. So that is it for all of homework number 19, or the cumulative practice problems for Unit 1, Lesson 19 of Illustrative Math Geometry.